was proposed by Hoyle and Gold in 1958 as a version of steady state theory, that in the steady state theory you can have galaxies formed in groups of 50 megaparsecs. So let's see how that comes about. The basic idea was that when matter is created continuously to make up for the matter which has diffused away by expansion, temperature of the universe to 10 to the power 9K. That is what it came out as a result of that. And if you ask in this hot universe how galaxies were formed, then you came out that if it is expanding, then with the help of expansion there is a steady state reached, and the typical size of galaxy formation was this 50 million parsecs, 50 megaparsecs. That means you will have blobs of, with the help of expansion there is a steady state reached, and the typical size of galaxy formation was this 50 million parsecs, 50 megaparsecs. That means you will have blobs of matter which is condensing into galaxies extending up to 50 megaparsecs. And these were called superclusters. And between clusters you will have empty space, so they would be called voids. So this idea was proposed. Here is the picture. You see here blobs are there, and in between there are gaps. There is no matter. This whole thing is expanding, so each blob is expanding and you will get this thing moving away from each other. So first generation is here, fourth generation is here. But the main point is that the universe is inhomogeneous on the scale of 50 megaparsecs with superclusters and voids. Now, this Hoyle said we should start with this model and try to work out what the source count would look like. So we used these assumptions. I won't go into details of this, but these assumptions were folded into our calculation, and we had something like 10 days to work out the answer because that date for presentation was there. We did not have any high-class computer to work out, so we had to use, literally we had these facet machines, hand-operated things, and if you felt like more adventure, you could go to the university's computer center, which had the EDSAC computer, which had the computer paper tape. So you got holes in the paper tape for each machine language instruction. If you made a mistake in giving the command, then you had to redo the whole thing. So it was a very nerve-wracking situation, and so we decided to not use the EDSAC, but use the desk calculators that were available, and we finally worked out a solution. Now there is some interesting anecdote that I should tell you here. We wanted to compare our result with what Ryle had got. So we went to, Hoyle asked Ryle, can you give us your data? So he was extremely reluctant to part with his data. He said, no, I can't give. So after great deal of talk to and fro, he said, okay, let's meet over tea. I will bring my curve, the thing that he had drawn. So he came there, and Hoyle and I went, and he produced a hand-drawn curve, and he said, this is the data we have, and that's all I can tell you. It gave some numbers written on that, and were required to work with that, because we did not have the formal data that he had collected, but he said, this is correct what I am giving you. Now, the anecdote part is that in general, Ryle was very sensitive about his data, and he didn't want to part with it, even to fellow radio astronomers, because he was afraid they will take the credit. So, whenever they came to tea in the Cavendish, they always left one man guarding their offices, so in case somebody goes and looks up on the table. So it was ridiculous to think that any scientist would stoop to that level, but Ryle was very paranoid about data. And I also remember that one radio astronomer who later on joined Fred Hoyle's Institute of Astronomy, Simon Mitton, he told us that when they had a group discussion, Ryle was extremely dictatorial, that everybody had to agree with what Ryle said. So this Simon Mitton was new to the whole group. So he did not know the result, the tradition that the group had with Ryle. So he began to object to certain statements. So Ryle got so angry with this opposition that he threw a paperweight at him. So all these things have come out in recent times in discussions. Anyway, so let us go back and to this thing. So does the steady state survive? So we produced a counter example, and Ryle, meanwhile, the Royal Astronomical Society said to Hoyle that you are going to get 10 minutes to reply to Ryle. Ryle was going to get 40 minutes to talk, and then comments were invited. So Hoyle discovered that the date of the meeting clashed with a lecture he was giving in London. So he said, look, I can't be present at that Royal Astronomical Society meeting, so you present our work. So he asked me to do that. So I was very scared at that time because, as you know, I was a raw research student. Although I had worked out this solution, I had no experience of how to speak in public or take part in a controversy. I had not given any research seminar. So I said, how am I going to manage it? So Hoyle said that if you think the calculation you have done is correct, then you should be able to defend it against anybody. So first you have to get into the frame of mind that you are right. If you trust yourself, then you go ahead. And he also coached me to speak, to give the answer within 8 minutes. He said there may be 2 minutes somebody raising objection or talking in the between, though he is not supposed to. So allow 2 minutes spare. And he said that many people, when asked to speak in a conference for 10 minutes, spend all the 10 minutes giving the background. And when it comes to their work, the chairman is already saying, your time is up. So they had to say, now my last transparency or something like this, and that last transparency goes on repeating. So this situation was there. So he trained me, and I gave a talk based on that at the RAS. We could show in our talk, or in my talk, I could show that we could get Ryle's slope of minus 1.8 without any difficulty because of local inhomogeneity, because of the voids region from which we are observing it. Now, at this meeting, there was another supporter of steady state theory, which was Hermann Bondi. Now Bondi was one of the creators of the steady state theory, so he was also challenged in the same way as Hoyle. So before the chairman or the president of the session called me to speak for 10 minutes, he asked Bondi, what do you think of Ryle's data? So Bondi gave a very sarcastic reply. He said that in 1957 he was getting a slope of minus 2.2 or minus 3. Then it came down to minus 2.2. Now he is saying minus 1.8. I am prepared to wait another 3 years. He will come down to minus 1.5. So this was, although people could see that the history was this way, but that was not giving a proper reply to Ryle in the sense that simply saying your work is not trustworthy. So here, when I finished, we could get into a situation where we can place random observers at different locations and compute the source count curves for all of them, and it is found that different observers get different answers because the universe is inhomogeneous, and you can get slopes ranging from minus 1.2 to 2, but all converge for low flux density to a Euclidean slope. So when we did present this all this work, there was a feeling in my mind that we should do this work given more time on a bigger computer, because in a computer you can create a universe by random generation of points, and you can put a random observer to look at this. So this was all done. In the subsequent year, Hoyle had got a computer from IBM in London. So he said this computer, IBM 7090, is a modern computer and we should work on that, use it. He bought some time on that computer. So that involved having punched cards. So we punched cards and took this packet of punch cards to London every Thursday or something. You go there at 10 o'clock, present those cards, then they won't allow you to run or take part in the computing. Their man will do it. So they would say, come after 3 hours, we will have run this and tell you what we got. So he would give these cards to them and come back after 3 hours. Either they would have detected some mistake in the program, in which case if it was a trivial one, they would correct it. Otherwise, we had to take the whole bunch back, study where we went wrong, do it right, come next Thursday. So this type of work was going on, and we patiently finally got the answer, and that is what I was saying, that you can get different slopes from different points. Now again I should tell you one feedback from our recent times. When Ayuka, our center in Pune, was being built, we had a temporary phase when the computer was located in one makeshift building. It was a prefab building, and people here are familiar with working in prefabs, so we did that. And the students were staying in another temporary location, which was about 200 meters. So they had to walk. So they started complaining, we have to go 200 meters to use the computers. So I told them my experience as a research student. I said, I used to go from Cambridge to London once a week and do it. So what is bothering you? So they accepted the point, and but it tells you how things have changed and the expectations have increased. So all this was done here. So the aftermath of that was the types of radio sources were analyzed further. Now I have put here what it says here, grapes and watermelons. Supposing you are asked to count the fruit in the market, you would, if you started just counting the grapes and watermelons together, you will get something which won't make much sense. But if you count grapes separately and watermelons separately, you will get some useful information about it. So what people realized that counting of radio sources which was being done in the earlier times was counting sources of various kinds which were not similar. And in fact, sources became more easily identifiable as quasars, blazars, and radio galaxies. There were different types of sources which radio astronomers realized should be counted separately. And counts are relevant if of populations of homogeneous composition. Otherwise, you cannot draw any conclusion. And counts tell us more about the sources than about cosmology, because people began to discover that how quasars are distributed, how galaxies are distributed, that determines and what their luminosity was, how was it changing with time, that determined the counts and not how the universe was expanding. So here you see 3C273, this is a source which has got a jet here. And if you look at it by radio astronomy, you again see a jet. So this is a quasar, and quasar means quasi-stellar radio source, and this was like a star. So it was so small that it was mistaken for a star to start with. And this is a huge radio source, two big blobs, and the distance here can be measured between of the order of thousands of parsecs that I was mentioning earlier. So here, what I showed in the previous slide would be a tiny dot. In other words, those were grapes and these are watermelons. So if you want to count them, you should count them separately. Now this happened in the following way, that because I had again a ringside seat when quasars were being discovered, so I would like to share with you that exciting phase. After this controversy with Ryle, two things happened. First of all, people said whatever you have done to save the steady state theory is correct, but is it the case that the universe is really so inhomogeneous? Does it have these big superclusters and voids? Because at that time there was very marginal evidence for it. But 20 years later, in the 1980s, people found that the superclusters and voids are there to stay. They are well confirmed because the telescopes were much more accurate and sensitive. So our assumptions in the 1960s turned out to be correct. Second thing was, Fred Hoyle decided that he should visit Jodrell Bank, which had a big radio observatory, and where people were studying the radio sources in a more systematic way. So they would like to examine the structure of a source rather than just count them. So we went there, and Hanbury Brown, who was the main person interested in radio galaxies, radio sources, he showed us all his data, the kind of treatment we could never get from the Cambridge radio astronomers. He showed everything, and he said that there were two kinds of sources, large ones and small ones. This just as I showed you here. And he said these little chaps, as he called these little chaps, that means small ones, what are they? They are very bright, but they are very small. And he said, they don't fit in our idea of a radio galaxy. So Fred Hoyle said that we ought to study their properties more carefully before drawing any conclusion on them. Otherwise, people would just start counting them, and again there will be a problem. So a arrangement was made. It was realized that one of the sources, the one which I showed earlier here, this one, 3C273, when it was first discovered, it was realized that it was occulted by the moon. That means moon goes past the radio source. So if you are observing the source will be blanked out while the moon is crossing it. And when the moon has come out again, the radio source will start, you will start getting the radiation. And because the moon's position is very accurately known, you will therefore know the position of the radio source very accurately. And that was done for 3C273, and it is described like this, that they took the observations at Parkes radio source, radio observatory in Australia, and then they got the data, and then they took it to Sydney. And because the data was expected to be very important, what they did was took 2 copies of it, and astronomers went by 2 separate planes from Parkes to Sydney, because in case the plane crashed and the whole data would. So it's a kind of macabre way of looking at things, but allowing for it. It just shows that they realized that it was a very important observation. And while this observation was done, they asked all the car drivers in the vicinity not to turn on their car radios, because that would interfere with the observation of radio astronomy there. So they obviously realized that what they were looking for is going to be very important, and they found this particular source, which is a quasar. And quasars were first discovered in 1963, and in this fashion 3C273 was one of the first quasar, and that gave rise to our various ideas of black hole and subsequent work on high energy astrophysics. So as I said, superclusters and voids have become an accepted norm, but the outcome of this was uncertain for steady state theory. That is, it was still allowed to function, but the steady state theory was ruled out for other reasons during this time. Ironically, the discovery of the cosmic microwave background ruled out the steady state theory. So what we felt was that a theory which has survived the first 4 points should somehow survive the 5th point also. So we have revived that theory into quasi-steady state cosmology, and that one allows you to, for other reasons, means those reasons are no longer applicable to this new version of steady state theory. So I will stop here telling you what happened during the stage when Ryle came out with this controversial statement, and how, although a raw research student and against Hoyle's general viewpoint, but with his own indication, I got into this controversy. Thank you very much.
Well, we have heard of controversies and learnings from them. So maybe you can ask more questions and create more controversies or solve more controversies if you like. Any questions, comments? Yes, you can take the mic.
Sir, you have also done a study on the microorganisms which you collected in the stratosphere. So, would you also
Well,
discuss some facts?
that's a different area in which I have worked in the recent years. This was to look for bacteria and possibly later on the viruses. If the assumption is that they are raining down on the earth from outside, we should be able to catch them at certain heights. So, optimum height range seems to be 40 to 50 kilometers, and we had a balloon facility, a balloon borne payload which went to 41 kilometers, and we collected air samples and they were brought down completely uncontaminated, and then they were given to biologists to examine, and they found bacteria in them, and also the bacteria survive ultraviolet radiation, which indicates that not similar to, I mean, they are different from what the bacteria here would be. So, our next job, which is still not sorted out, is to do some kind of isotope analysis to see whether carbon 14 carbon 12 ratio is the same as on the earth or different. And this is not so easy because bacteria are very small and very hard to detect where they are sitting, and you need micro beams, that is, the beams have to be very small to do this nuclear spotting. So, a lot of problems are there, but we are hoping someday we will be able to find an answer.
That time where paperwork, what you have done, how it was reported to the guide or to that competitive, controversial people?
How was it?
How was it reported? Did you publish it? How did you publish it? Did you first?
Yes, yes. This particular work was published as 2 papers in the monthly notices of Royal Astronomical Society. The first one was using analytical calculations, and the second one used the computer Monte Carlo simulations. So, both were published 1 year after the other.
Sir, tell us something about X-ray astronomy and its advantages over radio astronomy.
Oh, X-ray astronomy? Well, actually I should make a case for multi-wavelength astronomy. That means astronomy done with X-rays, gamma rays, then ultraviolet, optical, microwave, whatever wavelengths are available to you and can be used to probe. You can look at the same source with different wavelengths. You may get new information. Now, X-ray astronomy was mainly responsible for our discovery of black holes. The Cygnus X1 black hole was an X-ray source which contained a black hole. So, how this X-ray source arises is 2 objects go around each other, and one sucks the outer part from the other, and when it falls down, it radiates X-rays. So, that is how you discover this pair, and when you discover the pair, you find that you are only seeing one object going round, the other one is not seen. Then you suspect whether that other one is a neutron star or a black hole, and then examine, do some more testing and find out what it is. So, X-ray astronomy has its own advantages. It has contributed a lot. Radio astronomy has also contributed a lot. One can't say one astronomy is better than the other, but they are complementary.
Good afternoon, sir. Good afternoon. I'm from the field of meteorology, and working as a meteorologist.